Everyone, we're going to be doing some exercises with digraphs. We're going to start with example number 1. So for the digraph shown to the right, complete parts A through E below. Find the in degree and out degree of A. So we're going to look at A. In degree simply means how many arcs or edges with the arrows attached to them are pointing into A. So in degree is into. So we have 1, 2, 3. So our in degree is 3. We don't have any pointing away from A, so our out degree is 0. Next, we're going to move on to B. So find the in degree and out degree of C. So we're going to look at C. How many arrows are pointing into C? We only have 1. How many arrows are pointing out of C? 1, 2, 3 is the out degree. Lastly, we're going to look at D. What is the in degree of D? So we have 1, 2 arrows that are pointing in to D, and out we have 1 pointing out here and 1 pointing out here to E. So we have 2 out also. Now we're going to move on to finding the sum of the in degrees or the sum of the total out degrees. So the sum of the in degrees is simply just saying how many arrows are pointing into some vertex. So if we look at this graph, really all we need to know is how many arrows are there in general. So we only have 1, 2, 3, 4, 5, 6, 7, 8, 9 edges, meaning that there's going to be 9 arrows pointing into somewhere, and we're going to have 9 arrows pointing out. So 9 arcs in and 9 arcs out. Total of 9 arcs is the in degree and out degree. So now let's move on to if we don't have a physical graph drawn, instead of actually wasting our time and drawing a big graph, we're just going to look at the vertex set and the arc set and analyze the in degrees and out degrees from there. So if we're looking at C, we want to know the out degree of C. That means we're going to go from C to somewhere else. So when you have an arc set listed like this, it means that you're going to have an arrow from B to A, from B to C, from B to E, so forth and so on. So when we have an out degree of C, we want it from C to somewhere else. So we want C to be in the first spot. So how many times is C first? This is the only example where C comes first. We have one right here, but C is second. So that's actually going to be the next question. So the out degree of C is 1. Now we're going to look at the in degree of C. So in degree means that we're going to go from C or from somewhere to C. So we want C to be second. So where is C second? C is second when we go from B to C, and that is it. So our in degree of C is also going to be 1. Now let's look at A. So the out degree of A, again, we want out. A has to be in the first spot. So we actually don't have any arcs where A is first. So we're going to have an out degree of 0. And then we're going to have an in degree for A, means we're going to go from somewhere, and A is going to be second. So A is second here, here, and here. So we have 1, 2, 3. The in degree of A is 3. Okay, so for this example, we're going to try to figure out in this digraph all paths that are length 2 from B to A. So the first thing that we need is a path of length 2. This means we need to go down 2 arcs in order to get from B to A. So let's just try it. If we go from B straight to A, we're stuck at A. We can't get out of A because all of the arrows are in degree arrows. So we can't go down that because that's only 1 arc. So now we need 2 arcs. What happens if we go from B to D? Well, if we go B to D, that's number 1. Now we need to get 1 more arc to get from D to A, and there's not an arc directly from D to A. So we can't go down that one either. So the only one we could go down is B to C, and then we're at C, we need to get to A in 1 arc, so we go B, C, A. All right, the next one we're going to do is find all paths of length 3 from B to A. So now we're still trying to go from B to A. Well, if we go from B directly to A, we're stuck because remember we can't get out because everything's pointing in. So we can't do that one either. Well, what if we do B to C? So if we do B to C, the only 2 options we could have is we could either go straight to A or we could go up to B. So let's try B to C, and then we could go back up to B. So B, C, B. Now we need 1 more arc in order to get to A. Well, we could cover this one right here. So B, C, B, and then A. Now let's try the next one. What if we were to go from B to D, C, A, 1, 2, 3. So B, D, C, A. And then lastly, what if we were to just do B to D, then E, and then A? 1, 2, 3, we're good. So we did B, D, E, A. If you notice, if our path length is a length of 3, we're going to have 4 letters or 4 vertices listed. The same as if we were trying to find a path in the previous chapters. The path is always going to include the beginning and the end, so you're going to have one more than the length of that path. So find a path length of 4 from B to A. So we're not caring to find all of them, let's just find one of them from B to A. So we need to go from B to A in 4 edges. We could do 1, 2, 3, 4. So this would be B, D, E, C, A. Now let's try a length of 5. So now we need to go somewhere all around this graph and get back to A with 5 edges. So let's just try B to C, then C to B, 1, 2, 3, 4, 5. So we could do B, C, B, D, E, A. And we're not going to find all paths from A to B because that's going to be a lot. So we're going to skip that. Okay, now we're going to go over an example where we're going to try to find a path, but we're going to use a vertex set and the arc set to get from one to the other. So we're going to try to find a path from vertex E to vertex F. So we need to get from E all the way to F. And where is our E at? So we have an E right here. And then we have an F and an F right here. So how can we get from E to F? There's nothing that goes directly from E to F. So we're going to have to use some kind of middle vertex there. So we could go from E to D because that's the only thing that E is connected to. And then from D, can we go from D straight to F? Well, D has an arrow or an arc to F. So yes, so we could just do simply E to D and then D to F. Now it's asking for us to find a Hamilton path from vertex E to vertex F. So if you guys remember what Hamilton path is, it tells you right here. A Hamilton path is a path that passes through every vertex of the graph once. So that means that we have to touch every vertex of this graph. So we're going to have to go from A, B, C, D, E, and F. Well, we know we have to start at E and we have to end at F. So we can't go from E to anywhere except for D. So we know it's going to have to be E to D. That's the very first one that we have to go down. Now, from D, we have to get to everything else. Well, we don't want to go from D to F because then we're done. So we got to stop. First, we have to go to B, A, and C. Well, the only other place we can go to from D is D to B. So we're going to go D to B here. All right, and then once we go D to B, we're done with our D. We've touched the E and we've touched the B. So we still have to get A, C, and F. So we're now at B. Where can we go from B? Well, the only one that goes from B to anywhere is B to A. So we can go ahead and go to A. Once we go to A, now we have to get to C and then F lastly. So the only place we can go from A is A to C. And then we can go straight from C to our F. So for our vertex path, we're going to have E, D, B, A, C, F. I know my handwriting's a little bad over here. All right, now we're going to find a cycle in the digraph. So a cycle means that we're going to go from one vertice and get back to another vertice. So we want to get back to that same vertice. So where is one that has multiple letters? So we could go, let's just pick one. If we have B a couple of times here. So let's pick B. What if we start at B and we can go from B to A? Well, we can go from A to C, and then C, we can get back to B. So we could go B, A, C, and back to B. So that's a cycle because we can keep going around and around. Explain why vertex F cannot be part of a cycle. So when something is part of a cycle, so for example, if we have these vertices right here, let's say it looks like this. So we can go around this cycle. We can go this way over and over and over again. But if we're sitting right out here, we can only go this way. We can't go back to that spot. No matter how many times we go around that circle, we're stuck. We can't go there anymore. So if we look at a vertex such as F, so on F, the only time that we have F is C to F and D to F. So F has an n degree of 0 because nothing goes, has an n degree of 2 and an out degree of 0. The reason it has an out degree of 0 is because you can't go from F anywhere else. You can't go out from F. So because we have an out degree of 0, that means that you're stuck. Once you get there, you can't go anywhere else because you're stuck there. There's no way to get out. So that's why it cannot be part of a cycle. All right, now let's look at this last one. Consider the digraph shown to the right. Find all vertices that are incident to, incident from. All right, these are pretty much the same thing as saying in degree and out degree, but it's a little bit different terminology. So we don't really care about this word that says incident. We can just look at to and from. So find out vertices that are to E. So if we have E right here, what vertices or what other arrows are pointing to E? So this one right here is pointing towards E. So which vertice is incident to E? The incident to E is going to be C. So now we're going to look at incident from E. So we're going to go from E to somewhere else. So from E, we can go to D. And from E, we can go to A. So we have D and A. Or A and D, whichever you want to write it. All right. Now we're going to look at incident to D. So if we're sitting right here at D, how many ways can we get to D? So we can get to D from E, we can get to D from C, and we can get to D or towards D from B. Now, are there any ways that we can get from D to somewhere else? Well, we don't have a degree, an out degree of D, so because the out degree equals 0, we don't have any. So there's not any there. All right, so now we're going to look at our last ones. It's saying finding all the arcs that are adjacent to AC. So this is similar to when we had adjacent edges, except now we have arcs. So we're going to have to look at the direction of each of the edges. So let's switch to a color we haven't used yet. AC. If we have A to C, that's this arc right here. Where can we go from that C? If we're sitting right there at C, we can go from C to where? Well, we can go from C, let's choose this one. We can go from C to A, we can go from C to E, or to D, or to B. So our arc set that we could possibly go from on the A to C, because we're sitting right here at C, is going to be CA, CE, CD, and CB. Now, where are all the arcs adjacent to CD? So now we're going to look at the arc C to D. And where can we go from this D? We're sitting right here at D. What is adjacent? Are there any places that we can go from there? Well, this is an n degree and this is an n degree. So because D has an out degree of 0, we can't go anywhere. There aren't any. All right, well, that's it. Okay, so now we're going to look at example 6. Example 6 is asking us to create the digraph based on the table. So in this whole chapter, we're talking about having something that you need to get done, and we want to get it done in the most efficient way as possible. So we're going to have certain processors, and we're going to try to complete the task that we can go ahead and get out of the way, but sometimes it takes a little bit of time to do something before you do something else. So like if you're baking a cake, you have to put all the ingredients together and pour it in the pan before you can stick it in the oven and bake it. So we're going to do the same thing here. If you're starting with baking a cake, for example, are you going to try to put it in the oven first, or are you going to do the stuff that doesn't require you to do anything else, like gather all the ingredients? You can go ahead and do that, given you have them in your fridge. So what we're going to say is precedent task. So the precedent task just means what do you have to do before you do that task. So we're going to look at A. A doesn't have anything that you have to do. Neither does F or H. So we're going to start with these 3 tasks. So if we go right here, we're going to do S for start, and start is going to be 0 time because it doesn't take you any time to just like, hey, I'm going to start this. So we could go from S to A. And A takes us, we'll say 2 minutes. It's 2 units of time, but we don't know what kind of time it is. And then we're going to have F, because F is also blank right here. So F is 8 minutes. And then we're going to go from S to H, and H is 5 units of time, or 5 minutes. So now we've done all of our relations that don't require anything before it. Now where can we go from these places? So if we're at A, we've already finished A. So we finished A, well, we could go from A to C. So we're going to do C now. So let's say A was getting the ingredients, and then C is mixing the ingredients. So we're going to go A to C. C takes 3 minutes. Now, to go to C, we also have to do F first. So whatever F is, we're going to have to go from F to C. Now we've done A and F before we got to C. Where else could we go from F? So F could also go to B. Well, B only needs F to be completed, so we're going to put the 11 there. All right, now we've done everything for A, F, C, and B. We can go from H to G. So G is going to be 7. So now we have to move on. Now we've moved and we finished A, F, H, and let's say we finish C, B, and G. Well, where can we go from C? C is a precedence relation of E. So we could go from C to E. E is 4 minutes long. And then we have B and G. So we could go from G to D. So let's put our D right here. The only thing D has to have is G. And now we're done. We've done everything. So we've listed all of our letters. So now we can go to our end. Well, we could finish there, there, there. So we're going to do end. And end is also going to be 0. So now what we would do in this example is we'd go through all of our tasks and we'd figure out which one of the digraphs in the example matches what we've done. So now let's do another example. This is really important, being able to create the digraph based on the table. We're going to go a little bit quicker here, so let's use a color we can see. So we're going to go from our start, which is going to be 0, and the ones that don't have any preceding relations is A, F, and H. So we're going to write A, F, and H here. A has a time of 2, F has a time of 7, and H has a time of 5. So we're going to go create our digraph this way. Now we go from A to C. So we're going to put our C right here with a time of 2. We also go from F. So F has to be completed first. So we're going to go F to C. Then we could do F to B. So we're going to put that 10 right here. Now we've done all of these. We have H to G. Put G with 6. All right, now we finish all these. We finish C, B, and G. So we could go from C to E. So we're going to put an E with 5. And then we could go from G to D with 4. And we finished everything. So now we can take everything and move it to our end, which is 0. And we're done.